Hey guys, welcome to section 10.1, Parametric Equations. Now, parametric equations are just a simplistic way of being able to introduce another variable like time, but allow time to describe both an x and a y position. So let's just imagine a very simple scenario like this. That we have a parabola, a typical parabola, y equals x squared. Now, it would be interesting if this parabola actually represented u moving through time. So let's do the following. Let's set x and make it a function of t, and let's say, t minus 4. And then we'll make y of t equal to t minus 4 squared. Now you can see that if x represents t minus 4, then y is representing t minus 4 squared, or x squared. That this and this with this, they kind of say the same thing. It seems that these two are equal in a sense. But what's happened here is that it allows us to think of something moving along the path y equals x squared. So let's plot a couple of dots. Let's set t equal to 0. And we get x of 0 equals negative 4. And y of 0 is negative 4 squared, which is 16. And we have the dot at t equals 0, we have the point negative 4, 16. Now, we're going to let time move forward. Let's get t equal to 1. And so now x of 1 is negative 3, and y of 1 is negative 3 squared, which is 9. So 1, 2, 3. Here is the point minus 3, 9, and it's occurring at t equals 1. So what's happening is it seems that the parametric equation is watching these dots move along the y equals x squared. And by the time we get to, let's say, t equals 6, we've got x of 6 equals 2, and y of 6 equals 2 squared, which is 4. And here's the point. At t equals 6, we have the point 2, 4. This is called parametric equations. What we say that the parameter t is describing the motion on the x, y plane. So a lot of people actually write it this way. They put a t, they put an x, they put a y, and they go through that calculation. So we started with 0, we got minus 4 and 16, and then we did 1 and got minus 3, 9. And then the next one I did was 6, and we got 2, 4. And so it's really a table of 3 values. Now, the reason we like parametric equations is they can provide some complicated pictures that we traditionally haven't had before. So in a interesting fashion, rather. So let's just take and look at something like x of t equals 2 sine of t, and y of t is equal to 3 cosine of t. Now, you might wonder what that looks like, and so it's very reasonable to do some table values. Now, good table values are going to be table values that you can plug in into t here that the sine and cosine can be easily evaluated at. So I'm going to try some values that hopefully you guys know pretty quickly. I'm going to put in t equals 0, t equals pi fourths, t equals pi thirds, t equals pi halves. Let's see, t equals 2 pi thirds, and I'm going to jump to pi. So I'm going to graph a bunch of points. Now, a calculator would be good for this, but I want to be able to do these in my head. So the sine of 0 is 0, 2 times 0 is 0. The cosine of 0 is 1, 3 times 1 is 3. Sine of pi fourths is 1 over root 2, or root 2 over 2, times 2 will be root 2. Cosine root 2 over 2 times 3 will be 3 root 2 over 2. Pi thirds, the sine is square root of 3 over 2, times 2 will be square root of 3. Cosine of pi thirds is 1/2, so this will be 3/2. Pi half, sine is 1, it'll be 2. This has come down to 0. Now 2 pi thirds, if you don't memorize it, it's okay. Here's pi thirds, there's 2 pi thirds, so we're over here. The sine is still the positive value, so at pi thirds it was square root of 3 over 2, so at 2 pi thirds it's still square root of 3 over 2 times 2 is square root of 3. But the cosine now has become negative, which used to be 1/2 is now negative 1/2, so this will be negative 3/2. And then at pi we're over here, and the sine is 0 and the cosine is negative 1. So we've got a bunch of points. Let's plot them out and see what happens. So first off, at t equals 0, the point is 0, 3. X is 0, y is 3. So we're up here, and I'm going to put in here t equals 0. Now, the next point at time equals pi fourths is root 2 square root of 3, 3/2 square root of 2. That's 1.414, 4.2, 2 point something. So 1.4, 2 point something. Here's t equals pi fourths. All right, now at t equals pi thirds, we're going to go to square root of 3, which is 1.7, 1.5. Over 1.73 up 1.5. And now at pi halves, we've reached 2, 0. Now, what's happening is we seem to be going this way in time. Now, what's really interesting here is that we start going underneath, and we get over here at t equals pi. So I want you to notice we're just kind of orbiting something here. It would be nice if we knew what this was. It turns out that that is actually an ellipse. And now I'm going to show you how we know it's an ellipse, and it actually takes a total time of t equals 2 pi thirds, t equals 2 pi to see this happen. But before I actually prove that we know what this is, I want to demonstrate that we can see this on our calculator. I've got a TI-83 here. I'm going to go into the mode of parametric, which is the fourth option there. Let me pull that a little closer so you can see I've done parametric. And now I'm going to go to y equals. And if you notice the y equals, it's got an x of x1 t, y1 of t, so you can put more than one parametric equation. So I'm going to clear those two entries. And the first one I'm going to put in 2 sine t. And now the second one, oops, put it in the wrong spot, 2 sine t. And the second one I'm going to do 3 cosine t. Now, before I actually run it so we can see this happen, I'm going to go to another spot on the calculator. I'm going to go to the window, and the window allows for us to do a time step, so we can watch this parametrically happen. It just doesn't graph it all at once. And if you notice, it starts at 0 and goes to 6.28, which is 2 pi. It's going by a step of 0.3, so it's going to do not terribly many points. What are there, 60 points of step 0.13 around the circle? It's got an x-min of -4. Well, if we believe that, I probably can do a -3 to 3 for the x-min and max. And I got a y scale up to 4, so that looks like it's going to work out okay. So now I'm going to tell it to graph. And there it goes, it graphed it. Now, unfortunately, it kind of looks like a circle because the I only have 3 steps right and left, 4 up and down. It's been stretched inappropriately. So if I want the same measurement of sides there, I actually have to tell it that the X window needs to be something like 6 to 6. And then when I graph it, we can see the oval better. And now you can see that the step size horizontally and vertically are almost the same. But it's produced an ellipse. Now if you want to see it done slower, we can have the steps take place much, much slower by taking more of them. So this time I'll do about half the speed, and I'll tell it to graph. And so now we're seeing it being parametrically created slower. Now what's neat about parametric equations is you can control the direction that things move. So if I go to my y equals and I actually change the t to a minus t, now this could actually change the starting point, but in some sense I'm running time backwards, which means when I graph it, it goes the other way around the circle. So by an appropriate choice of time and a linear transformation on time within the function, it's possible to start at different points and move periodically around this ellipse. Now, why is this an ellipse? Well, we have 2 equations, and anytime you have 2 equations, you should be interested in saying, oh, let's manipulate them. So I'm going to take x squared, and I'm going to drop the parentheses t because it's not really important to know it's a function. To write that it's a function, we know it's a function. Well, that's going to be 4 sine squared of t. And then if I divide by 4, that says x squared over 4 is sine squared of t. Now, doing the same thing with y, I can easily get y squared over 9 equals cosine squared of t. And now I know a relationship that when you add sine squared and cosine squared, you get 1. And why, lo and behold, I get the equation x squared over 4 plus y squared over 9 equals 1. And this is called the standard form of a hyperbola. In fact, not a hyperbola, sorry, an ellipse. And it's easy to see why, because if x is ever bigger than 2, this can't be equal to 1 because this is positive, so x is clearly bounded between minus 2 and 2. And when x is at 2 and minus 2, this equals 1, so y has to be 0, so these 2 points are really easy to spot. Same thing with y equals 3 and minus 3. That makes it already equal to 1, so x has to be 0, and these 2 points are easy to spot. And we have an equation for an ellipse. So, parametric equations. Well, what can we do with them? Well, the power of a parametric equation is literally the power of a spirograph. And if you've ever seen it, it is possible to create crazy looking functions. So I am going to put in one of the ones out of the book that's pretty funky. It's on page 643. And the equation is by no means simplistic. So the first one is 2.3 times cosine, and they do a multiplier of t by 10, and then they add on the cosine, and then a multiplier of 23 times time, and then the y, they do 2.3 times sine of 10t, minus the sine of 23t. Now, it turns out that with some trigonometry that it is possible to observe that this 10t in both the x and, oops, I missed a 10t in the sine one here. Got to put a 10 in front of it. So now, if you have a 10t, a cosine 10t inside of the sine, a 23 in the cosine, 23 in the sine, you're going to have a periodic function here. But it's not clear how big this function is going to take on the values, what it's going to do. But here's a couple of things that are pretty easy to see. You know sine and cosine are bounded by 1, so clearly x can't be bigger than 3.3 or less than 3.3. Well, 2.3 plus 1. Yep. So I'm going to put in an x bound and a y bound of 4. Now when I say an x bound and y bound of 4, that's to the right and to the left 4. And so now I'm going to have it graph and oh my goodness, it's like a 46 pointed star or something. Pretty crazy, huh? All right. So we can create wild and interesting patterns. Now, it's just not wanting to create patterns. It's actually wanting to describe life a little bit. So here's a really interesting thing that if you've ever ridden your bike when you're young at night, these kids that have a light on their bicycle, yeah, I'm not a good bicycle drawer. Here's my person with his feet. Now, if the light is located right at the rim of the tire, as you go forward, the light is going to go up all the way to the height. Now the wheel has moved forward, and now it comes down and hits the ground when that wheel comes and hits the ground again, and it repeats. So we have this shape that's bouncing along down the road. Now there's other shapes that's like this. Imagine if the light had been a little bit above the ground. Well, then it actually could do something like this. And so we'd maybe like to understand how normal motion creates parametric effects that we could take a look at. Now, before we start looking at too many of these parametric effects, let's just realize that there's a couple of standard parametric equations that we see a lot of. The first is the ellipse that we looked at, and that's an x of t equal to an a sine of t, and y of t equals a b cosine of t. Now, if you like, you can make them spin faster or slower by putting a multiplier of t. So an alternate way is this x of t could be some a sine of kt, and y of t equals b cosine of kt. So long as we have the same k there, then sine squared and cosine squared can be mixed together. But the minute you change 1 to k and 1 to m, you start getting these strange spiroscopic effects. Now, you can also put cosine first and sine second, and that will go around a circle. Which direction you should test and find out. Ellipse. Now, if you want a circle, then you just set a equal to b. So if a equals to b, it's a circle. And the radius is equal to a. Well, are there other interesting figures that come out of parametric ones? Well, one is simply called the simple parametrization. And that is, any time you write y equals an f of x, you can do a trivial parametrization, and you can set x of t equal to t and y of t equal to the f of t, and you are drawing this function parametrically. And that's what I did first. We walked through and drew a function parametrically. Now, sometimes it's not that trivial, and you'd like maybe to know what's going on. So what happens if somebody said, well, I've got this x of t, it's t squared plus 2, and I've got this y of t, which is 7t minus 3. Now, you might wonder what that looks like. The parametric one can draw, but maybe you want a more concrete description. Well, one thing is to see if you can come up with a way to make the t's common enough that they can be substituted into each other, or actually maybe even solve for t. So let me show you that in this one here, I can take the y equation and write y plus 3 over 7 equals t. And then I can put that into the x equation, and we're going to get x equals y plus 3 over 7 squared plus 2. And now you're actually going to discover that this is a parabola that's horizontal. So it's a horizontal parabola. I can see it this way because if I just switch x and y in my head, I know that y equals x plus 3 over 7 squared plus 2 is a parabola. So I can check this out two ways. First, instead of looking at it this way, I can go to my graph parametrically. And I can say, let's put this in. Let's put x of t equals t squared plus 2. And then y of t, I'm going to make 7t minus 3. And now I want my window big enough so I can actually see this parabola. And so notice x has definitely got to be positive here. So my window here, I'm going to make it go up to like 25, a step of 0.1, x min at 0, x max at, let's say, I don't have to go by 25 at all. I can go like to 5. So I'll use 0.05. Y min I'll put at -4, and y max I'm going to put at, it's y max I can put at like 55. I got to go to x max to like 60. All right. Let's do a graph. Now, notice I just got part of the parabola. Now, how do I get the rest of it? Well, I need to find the right units of time. Time started there and went that way. So if I go to my window, maybe I should start time equals -5 and go to 5 and graph it. And oh, now I see it come there, but I can't see the bottom, so now I got to do the y. Let's do y min of -55, y max of 55. Now graph it. Oh, and now we're seeing it happen. And we're starting to see our parabola that was on its side. So, what is the method by which we can identify these things if they're in parametric form? It's not done so commonly, but we often ask students to do that. And that's when things can be somehow solved. But solving is by no means a straightforward process. Suppose we're looking at this parametric equation and I want to know how they're related just in x and y and don't have the parameter in there. Well, I'm going to make x minus 8, that's t cubed. I'm going to square that and say x minus 8 squared is t to the 6th. Then I'm going to take y plus 2 is equal to t squared. I'm going to cube that, and y plus 2 cubed is t to the 6th. And now I've discovered that x minus 8 squared is y plus 2 cubed. Now, what good that is, that's not at all clear why we'd want to do this. This is probably a wonderful image, or at least it describes a point moving through space. The important thing here is that the idea is the parametric equations are going to be used to represent as something happens in time. Now, last but not least, I need to point out that some parametric equations do things that are strange. They seem to be disrupted on the one side versus another. In other words, if they use functions that have asymptotes or have unusual values in them, then the pictures can actually be multi-parted. They can look absolutely crazy. So one of the ones I'm going to do is one that's got a loop, and in addition to the loop, it's got a second piece to it that's not part of it. So I'm going to write down ax equals minus 1/2 plus cosine of t, and then y equals minus 1/2 tangent of t. Now this is going to provide the discontinuity at pi halves plus sine of t. This discontinuity that exists here at minus pi halves, at pi halves, at 3 pi halves, has the potential to break this function when drawn into pieces. So let's see what happens. Let's see if it does that. So we're going to take a minus 0.5 plus cosine of t, and we're going to take a minus 0.5 tangent of t plus sine of t. And now I'm going to make sure that I use a pretty vast values of t here so I can see if there's more parts to this than meets the eye. So I'm going to let t go from like minus 24 to 24. Why? Because I want to get some of those asymptotes involved in it at minus pi halves, pi halves. Minus pi halves is less than 1. I can do minus 3 to 3. Oh my goodness. Minus 3 to 3. That'll get some of the asymptotes. Good step size. Let's do a negative 10 to 10. I have no idea, without looking at it, what the range of x might be. Actually, I can see that right away. Cosine varies between minus 1 and 1, so the x's don't have to be very large. The x's can be limited to about minus 2 to 2. Now, the y's can get quite large. They can get infinitely large, in fact, negatively infinitely large. So on the y's, I'm going to leave that minus 55 to 55. So let's give this a shot and see what it gives us for a graph. Oh, that was pretty funky. There's some whipping and stuff going on there. Now I know where to look at here, so let's zoom in on that number. I have a feeling that's really close to minus pi halves, so I'm going to go to my window here, and I'm going to stay very, very close to minus pi halves. I'm going to try minus 1.8 and just minus 1.8 and go just to 0. And I'm going to use a much smaller, oops, I still want the lots of t values in there. Sorry, I was the wrong place to go there. Minus 3 to 3 in the t values. The x values, I'm going to start at minus 1.8 and go just to 0. And obviously the 55 was really quite large, so let's try minus 5 to 5, see if that helps. And now we're going to do the graph. There we go. Yeah, and it does something crazy, and it actually is very possible that it's doing a loop there that we want to zoom in and look at, but it looks like we've got this strange path here and a loop over here. It's actually broken in 2 pieces, and it has some very strange properties. Would it be good to solve for this rectilinearly, to put it in x and as a function of y? It probably is impossible, because you can see it doesn't pass the vertical line test. So the parametric equation, for whatever reason that came into existence, was probably a description of something. All right.